So welcome back to the lecture on two-dimensional motion and vectors. So in this lecture, we'll continue our lecture on projectile motion now. So what does projectile motion mean here? So in this lecture, we're going to discuss the objectives of this section will be, we'll try to recognize examples of projectile motion, describe the path of a projectile as a parabola, and finally try to resolve vectors into their components and apply the kinematic equations to solve problems involving projectile motion. So let's start with projectiles. What is a projectile? So any object that is thrown or launched into the air and is subject to gravity are generally called projectiles. So projectile motion in simple sense is a curved path that objects follows when it is thrown, launched, or otherwise projected near the surface of the earth. Now, when you remove the air resistance, the projectiles generally follow a parabolic trajectory. So this is an example here. So let's take an example of a ball that is thrown horizontally with a certain velocity. And let's say they have a ball that is being freely falling. Now, the idea here is that at any single point of time, when you look at the vertical motion of a freely falling body and a body projected with an initial velocity, both of them travel at the same time to the ground. The reason mainly is because the vertical motion is being controlled by the acceleration due to gravity, and the horizontal motion does not have any acceleration. So the horizontal motion is a constant velocity motion. So because it's constant velocity, the acceleration along the x direction is 0, but the acceleration along the y direction equals plus g. So here the acceleration along y direction is plus g. Here vi is 0. And therefore ax will also be 0. Because both of them have the same vertical motion being controlled by the same vertical parameter, that's the reason why they drop, both of them will fall to the ground at the same rate. So always remember that when you have a horizontal velocity of a projectile will always be considered constant. The reason we consider this constant is because we do not account any air resistance. If you account air resistance, there might be a chance that we might consider horizontal velocity, but as of now we do not need to consider any changes in the horizontal velocity. So let's start with the kinematic equations. So how can you know the displacement, velocity and acceleration of a projectile at any point in time during its flight? So one of these methods is to resolve the vectors into components and thereby apply the one-dimensional form of equations for each of these components. So finally, when you want the resultant, we recombine the results to determine the resultant. So the idea here is that, for example, let's consider that you have a projectile motion. So projectile motion is a body being projected upwards with this velocity vi. So let's consider that this is the projectile. So it started at this point here and this is the end point. So what are the parameters that we need to know? First parameter is the maximum height that it can reach, and the second parameter is the maximum horizontal distance. This maximum horizontal distance traveled by a projectile is generally called range. And at any single point of time, notice that this is the velocity vi. So to find out height and range at the same time, we cannot do that. So what you would do here is we'll resolve this vi into vi of the x component and vi of the y component. So we split it into its individual components. Now, when you look at it from the top, this way, so the motion is basically a horizontal motion. So this motion basically is a horizontal motion. So where the body starts at this point here, this is the point A. Let's consider this point here and this point B. And this point B right here. So it's a horizontal path, because notice that from the top you don't see the actual position, actual height. Now let's look at it from the side. When you look at it from the side this way, you're basically noticing the path going upward. So this is the point A here. And let's consider that the height point is C. So this body A travels to the point C here and then comes back to the point B here. So this is the vertical motion in terms of to the side. Notice that when you look at it from the side, you do not notice any horizontal motion, you only notice the vertical motion. So this splitting is basically resolution. So where we solve this using the x component quantities and we solve this using the y component quantities. So what is the x component, y component quantities that we're going to use is the velocity itself. So we use the velocity itself as the main point to calculate these values. So when you have a projectile that is launched horizontally, so the chances are its initial vertical velocity is always going to be 0, and its initial horizontal velocity is the initial velocity. Now when you have a projectile that is launched at an angle, we'll try to resolve the initial velocity into x and y components, and we'll try to consider that the initial vertical velocity is the y component and the initial horizontal velocity is the x component. So we are basically splitting this vi into vxi and vyi. So let's take an example and try to solve this problem. So a zookeeper finds an escaped monkey hanging from a light pole. Aiming her tranquilizer gun at the monkey, she kneels 10 meters from the light pole, which is 5 meters high. The tip of her gun is 1 meter above the ground. At the same moment that the monkey drops a banana, the zookeeper shoots. If the dart travels at 50 meters per second, will the dart hit the monkey, the banana, or neither one? So let's try to consider a simple diagram of this particular topic here. So let's say that you notice, so in the problem it's mentioned that the zookeeper is aiming from a height of 1 meter. So let's consider this distance here is 1 meter. Now the monkey has climbed a pole 5 meters high. So let's consider that this here is 5 meters. So this is the pole 5 meters. Notice that this is the line of sight for the zookeeper. So which means that this distance becomes 1 meter. So this is 1 meter. This is 5 meters. So which means that this becomes 1 meter. So this distance becomes 1 meter. And this distance here is 4 meters. Now he's aiming the gun at the monkey. So his velocity the velocity with which he is trying to project it is in this direction. So this is the initial velocity with which he is trying to fire the gun. Now she kneels 10 meters from the light pole. So which means that this distance here. So she kneels 10 meters from the light pole. So this is 10 meters. So we have everything that we need. So notice that she is aiming her shot at the monkey. For example, let's consider this is the position of the monkey right here. And this is the zookeeper right here. Now if the dart travels at 50 meters per second, so this vi is 50 meters per second. So what is happening here? At the same moment the monkey drops a banana. So what is happening here? At the moment when she shoots, the monkey drops a banana. So the zookeeper will shoot. Now if the dart travels at 50 meters per second, will the dart hit the monkey, the banana, or neither one? So let's try and understand this particular problem right here. First thing that we need to know is this angle right here, this angle theta. So we have the right angle triangle here. Notice that this is 90 degrees. So this is 4 meters and this is 10 meters. So from this we can write tan theta, which is opposite side, which is 4 meters, divided by the adjacent side, 10 meters. So theta becomes tan inverse of 0.4. So use your calculator and calculate tan inverse of 0.4. So let me find tan inverse of 0.4. So that value becomes 21.8 degrees. So this angle right here is 21.8 degrees. Now we have the angle right now. The next one that we want to do here is to choose the kinematic equation to solve for the time. So notice that at this point when the monkey drops the banana, it travels at a certain velocity downward. Now this dart will take certain time from traveling from here onto the monkey. So let's look at the total time it takes to travel in total. So how much time will it take? So now we have the angle. So the next thing we want to calculate is the time. So let's consider the horizontal velocity part first. So the horizontal, in horizontal direction, so let's consider the horizontal component first. So in the horizontal component, the velocity is the x component of the velocity here, so which becomes v cos theta. So v here is 50 cos 21.8 degrees. Next, acceleration ax is 0, and the delta t is the time of flight, right? So this is the time of flight. Time of flight basically means the amount of time that it takes to reach the ground. Next, delta x is the total horizontal distance. So this is, let's consider this horizontal distance. Let's not call this total horizontal distance. So this is the horizontal distance. Now let's try and find the equation. So we know the equation delta x equals vi times delta t plus half into a times delta t square. So substitute the values. So vi here is vxi, so which is 50 cos 21.8 degrees times delta t is delta t, because we do not know time here yet. Now we know the horizontal distance. That horizontal distance is 10 meters. So from this, delta t becomes 10 meters divided by 50 cos 21.8 degrees. So that value becomes 0.215 second. So this is the total time taken, 0.215 second. So now we have calculated the time. Next, we want to know the vertical distance. Notice that first thing that we know of the total dart is it is going to go travel 10 meters. Next, it has to travel, we need to know the vertical distance. So delta y of the banana. So notice that the monkey is dropping the banana from this point right here. From the ground, it's about 5 meters high. So when you're traveling about the vertical direction, we know that the acceleration a becomes negative g. So acceleration a becomes g. Now, so that is 9.81 meter per second. Next, we know that the initial velocity is 0. And we already know the total time it takes. So the total time it takes here is 0.215 seconds. Notice that at the same time, so in the question it says that at the same moment the monkey drops a banana, the zookeeper shoots. So that's the exact same time. So by the time the dart travels 0.215 seconds, we want to know what is the position of the banana. So we are going to consider that time itself as our answer. So from this, delta y becomes, we know that it's vi into delta t plus half a into delta t square. So vi is already 0, so becomes half ay into delta t square. Half times ay is 9.81 times delta t here is 0.215 square. So that distance becomes 0.227 meters. Now notice that the distance that it has traveled from here until here, so in that amount of time, is 0.227 meters. So because it's traveling downwards, so let's consider that this distance is negative. Now we have to know what is the dart. So how much distance has the dart going to travel vertically in that amount of time. Notice that this is the same amount of time we're going to take. Now in that amount of time, so we have vy I into delta t plus half into ay into delta t square. So vy times I here, because vy here, vy times chi can be written as vi sine theta into delta t plus half ay times delta t square. So the time will not change. So vi sine theta here is 50 sine 21.8 degrees times 0.215 plus half times 9.81 times 0.215 square. So when you calculate the total value, that value becomes a total of, so notice that here the dot traveling is the reverse direction, so ay here becomes negative g. So ay here becomes negative g. So from that we have 3.99 meters minus 0.227 meters. So that value becomes 3.76 meters. Now this is the dot. So for the final height of the banana and the dot, both the banana and the dot, so what's going to happen here is, notice that the dot will reach a height of 3.76 meters. So from this point right here, from this point, it reaches a height of 3.76 meters. So it goes upward 3.76 meters. So let's consider that point right here. So that point right here will become from the ground, that point is 4.76 meters. So let's consider the actual position here. So the final height of the banana becomes the final height of the banana initial with respect to from the top to delta yb. Delta yb here is the change that is happening here. So the total height is 5 meters from the ground. So notice that we are calculating the position of the banana from the ground. So delta yb here is the amount of distance that it traveled in the reverse direction. In the reverse it has traveled negative 0.227. So that distance becomes 4.77 meters above the ground. So this is the position of the banana, final position of the banana from the ground, above the ground. Now with respect to dot, so what is the position of the dot, final position of the dot? Now again, dot initially plus delta yd. Now it's already at a height, so the zookeeper is already shooting at a height of 1 meter. So that's 1 meter plus, it has traveled above the 1 meter, it's going to travel 3.76 meters. So 1 meter plus 3.76 meters, so that is going to be 4.76 meters above the ground. So if you round off the values, they are nearly the same, so which means that the dot here will hits the banana. So when you round off the actual values, notice that these values are really close. So it basically means that the slight difference is due to the rounding that we have done. So therefore the dot finally will hit the banana. So this is how you can solve problems involving projectile motion. So use the same principle now. Pause the video right here and try to solve this problem. Next, let's go to the next section, relative motion. So in this section, we're going to describe the situations in terms of frames of reference and finally solve problems involving relative velocity. Now, let's consider what is the term frame of reference here mean. Let's say that you're traveling at 80 kilometers per hour north and a car passes you going 90 kilometers per hour. So here, when you're looking at the faster car is moving north with respect to you only at 10 kilometers per hour. With respect to you, is not moving at 90 kilometers per hour. So the only way you know that he's traveling 90 kilometers per hour is because somebody on the ground who is stationary sees him traveling at 90 kilometers per hour. So your velocity and his velocity are based on the reference of a stationary object on the ground. So with respect to the person traveling at 90 kilometers per hour, you're only traveling 10 kilometers per hour less than him. To you, he's traveling at 10 kilometers per hour more than you. So whenever somebody is standing on the side of the road, would measure the velocity of the faster car as 90 kilometers per hour towards the north. So for you, he's traveling only at 10 kilometers per hour. So this simple example is basically the understanding of what a frame of reference means. So for a frame of reference here, for you to be the frame of reference, he's traveling, if you're the frame of reference, he's traveling at 10 kilometers per hour. But if a person standing on the road is this frame of reference, he's traveling at 90 kilometers per hour. This difference in the frame of reference determines the velocity with which a person is moving on the ground. So let's say you have consider a stunt dummy dropped from a plane. So when you view from the plane, the stunt dummy flaunts straight down. So when you're going on the plane, the stunt dummy is basically going downward, but with respect to you, it's traveling at the same velocity forward as you're going forward. But for a person standing stationary on the ground, this is what he would see. He would see a curved path where the stunt dummy hits the ground, but you would be traveling with the same velocity forward in this direction. The main reason this will not be able to travel is because the plane is opposing the gravity, but here the stunt dummy is not opposing the gravity. That's why it falls to the ground. But in terms of the vertical direction, you're traveling at the same intervals of time. You're not changing the intervals of time horizontally. So that here is the example of relative motion. So relative motion is generally described by using subscripts. For example, if you consider the example before, so we have two cars, one is the slower car, but one is the faster car. So the velocity of the slower car with respect to the earth is 80 kilometers per hour north. The velocity of the fast car with respect to the earth is plus 90 kilometers per hour. So the unknown that we do not know is velocity of the fast car with respect to the slow car. So we write it as VFS. So VFS represents where F represents the one that you are starting with, and S is the one that you are ending it with. So VFS becomes VFE plus VES. So we use the principle of velocities here. So we use the principle of vectors here to determine what is this velocity here. So how do you calculate VES? ES is the opposite of SE. So if VES becomes minus VSE, so when you calculate VFS, it becomes VFE plus VES. So we know that VES is minus VSE, so we can write it as VFE minus VSE. So velocity of the fast car with respect to the slow car becomes plus 10 kilometers per hour. Now the principle, remember this formula, VAC is VAB plus VBC. So this is the general form of a relative velocity equation that we generally use. So let's take a simple example of this principle and try to demonstrate this principle. Right? So let's try and use this problem to demonstrate the actual issue here. So what is given here? So you have a boat that is heading north, crosses a wide river with a velocity of 10 kilometers per hour relative to the water. So the river has a uniform velocity of 5 kilometers per hour due east. Determine the boat's velocity with respect to an observer on the shore. So now let's try and visualize this. So let's consider that this is a river. So the river is flowing east. So the river is flowing east. So this is the river flowing east, and a boat is trying to cross a river, and it's trying to go towards the north. So this is the direction in which the boat is trying to go, but the water is traveling with a velocity here, so which means that this water here is traveling with the velocity. Now they are asking us to calculate the water velocity of the boat with respect to an observer on the ground. Now try to draw a simple vector diagram. So let's consider that this is the velocity of the boat with respect to the water, and this is the velocity of the water with respect to the earth. So what they're asking us to find is this vector here. So they're asking us to find this vector right here. So this is the velocity of the boat with respect to the water, the velocity of the water with respect to the earth. They're asking us to find the velocity of boat with respect to the earth. Now we know that from vector addition, we can write that VBE here is VBW plus VWE. So this is a vector addition, so which means that this cannot be done directly. So we have to calculate VBE here. For calculating VBE, first thing that we need to know is this angle theta right here. So for knowing that theta, they have given us VBW, so which is 10 kilometers per hour, and VWE is given, so which is 5 kilometers per hour. So from that, first let's try and calculate theta. So from the Pythagorean theorem, we know that this is 90 degrees. So from the Pythagoras theorem, we can write that VBE square equals VBW square plus VWE square. So VBE square equals VBW square plus VWE square. Notice that this is vector addition. So I'm not going to write this just in case so that you don't get confused. Now let's try and solve this problem right here. So what do you have left here? So VBE square equals VBW square is 10 square plus 5 square. So which is 100 plus 25. So which is 125. So VBE square. VBE becomes under root 125. So which when you put it clearly, so that value becomes 11.18 kilometers per hour. So this is the velocity of the boat with respect to the earth. Now notice that the boat is going north, the river is flowing east, so this is going northeast. But we need to know the angle as well. So that angle can be found using tan theta. Tan theta becomes VWE by VBW. So VWE is 5 over 10. So which is 1 by 2. So theta becomes tan inverse of 0.5. So that value becomes 26.6 degrees. So the angle here is 26.6 degrees. So we can write that the boat, so VBE is 11.18 kilometers per hour. So which is kilometers per hour in the direction of, so the theta here is 26.6 degrees northeast. So this is the answer for your final problem. So use the same principle now. Pause the video right here and try to solve this problem. So with that, we end our lecture on two-dimensional motion and vectors. So I will see you again in the next lecture.